I would like to clarify that I filmed Tuesday's lesson and today's lesson on the same day, so I am not wearing the same clothes that I wore on Tuesday. I'm filming them all on the same day. That is also why my fingers are blue, because the vis-a-vis that I wiped off of those last sheets dyed my fingers. So first, just a reminder of what we did on Tuesday, that we were finding the derivative of natural log and it ended up being 1 over x, or really as we found that we were taking the derivative of x here, or the derivative of u, and then over itself. Always making sure that our domain makes sense for the problem. For our natural logs, that u or x would have to be greater than 0, so we want that to be true of our derivatives as well. I don't think I did a very good job of reiterating that on the extra problems that we did on the practice problems. So do note that that is going to be true no matter what. If we're dealing with natural log, we want to make sure the domain makes sense. So today we are going to make like Carrie Underwood, if you know what I mean. And we'll be finding the integrals, the antiderivatives. So if I start with my 1 over x and I'm finding the antiderivative, I am going to end up with what I started with on the other ones. So I am going to end up with natural log. But then I still have this issue of making sure that the domain makes sense. And they won't always guarantee with this that the x was greater than 0. So what we're going to do is just make sure that the x is greater than 0 by saying that it's the natural log of that x. And then always plus c. If we're dealing with something a little bit different, a little bit more complicated, then we'll have a 1 over u du. And same situation is going to happen here. I'm going to end up with the natural log of u plus c. You might be wondering what happened to the u prime over u, because that is what we ended up with for the derivative of natural log of u. But we do actually have the derivative of u right here. So this actually is the derivative of u over u, just like this is the derivative of x over x. So that notation is really important. It makes it all make sense. So some hints when we start finding the integrals here is to use u substitution when it makes sense. So where it's going to make sense is when we're bigger on bottom. And you'll see why in a minute, but if it's bigger on bottom, that's going to mean that when I use u substitution, the derivative of the denominator is going to end up being the numerator, so it'll end up looking like this. So if it's bigger on bottom, we want to use u sub. If it's bigger on top, then we want to go ahead and divide. And in the moment, it might seem like dividing is not a good idea because it might make it uglier to begin with, but it's actually still going to be easier to work with. So we'll just say, even if there's a remainder, it's still going to be easier to work with. I also want to mention that you might think that we have done something like this before, finding the integral of 1 over x, because it looks so simple. It looks like something maybe we had done before, where we move the x to the numerator and change that power to a -1. But if we did do this, think about the power rule. So when we integrate x to the negative first, we would be raising it a power, so we'd get x to the 0 divided by 0. Okay, so this is the reason that we end up with something for the integral that is not really normal, because if we did use our regular power rule, it just doesn't work. You end up with something that is undefined. So starting with our first example, we can think through the hints that I had there of if it's bigger on bottom or if it's bigger on top. But also remember that anytime I'm using u substitution, I have to make sure I can find the derivative somewhere in that problem or create the derivative somehow. So if I did choose my x squared plus 2x plus 3 to be my u, there isn't a way that I can make that du appear, because my du is going to be this 2x to the first plus 2, And so now I'm going to be left with my x to the third. I'm going to be left with my x squared, and that's just going to be really gross. So yes, my hint said if it's bigger on bottom to use substitution for this, but also just thinking through substitution, it makes sense that if I take my denominator, yes, it's going to have an x to the second in it. It's going to have a derivative of this is an x to the first. So we're going to go and let u be the denominator. Taking the derivative of that, we find that du is 3x squared plus 6x plus 9 dx. And then remember, we're always trying to make that happen. So it may not look exactly like that, but we have all of the x values. We've got our x squared and we've got our x in there. So we're trying to think of ways that we can manipulate this to look like our du. And you might notice that if we multiplied all of these by 3, so I'd end up with a 3x squared, a 6x, and a 9, and that's exactly what I need. So what we're going to do over here is we're going to go ahead and multiply the whole thing by 3 over 3. Remember, we can put it wherever we need to, so we're going to put the 1 3 with the numerator. The other one is just going to hang out the 1/3 out front. And if I go ahead and distribute my 3 to the numerator, I can see that it does end up looking exactly like I need it to. That is a good time right there. So we end up with the whole numerator and dx being the du. My denominator is my u. So I'm going to go ahead and do substitution here. So I've got my 1 over u, and then this whole thing becomes du. And now this is what we were looking for, the integral of 1 over u du, which we just learned. So we're going to have that natural log of u, absolute value u, plus c. And then remember, we always want to plug that u back in. So this is going to end up looking a lot more complicated than we've got it. Our 1/3 natural log of the absolute value of x to the third plus 3x squared plus 9x plus c. Ooh. Now for something that is bigger on top. So something to notice here is that if I am using substitution, I would want to choose the higher power so that I could get a derivative that makes sense. But the derivative of this is going to have that 4x cubed in it, and I don't have an x cubed anywhere else in my problem. So with either of these, if I try to make the numerator the u, if I try to make the denominator the u, I'm going to end up with a lot of loose ends and not have a way of finding the whole du in order to replace my whatever dx with du. So instead of doing substitution right away, this is that bigger on top that we're going to go ahead and divide the denominator into the numerator. If the denominator looked like x plus 2 and not the x squared, then we could use synthetic division, but since it is an x squared, we are going to use long division. I know we don't necessarily like long division, but long division likes you. So remember in long division that we're thinking of what we could multiply x squared by to get that x to the fourth. So just looking at the first term. So I'd say, okay, I can multiply it by x squared to get as close as I can there. I'm going to multiply my x squared times x squared and then 2 times x squared. And it doesn't really matter that there's not an x squared, I'm just going to add it to nothing. And then remember with long division, you're always changing the signs or subtracting. So I'm going to get a negative 2x squared plus my x minus 4. Same thing again, what I can multiply x squared by to get my negative 2x squared. Sorry, that's not too clear. So I want to multiply it by a negative 2. It's going to give me a negative 2x squared. I want to match it exactly, so negative, we'll have it have a negative. And then negative 4. I'm going to be changing the signs. So I get nothing here, I get my x, and then nothing there. So my remainder on this is x, and that's okay. It's just going to mean that I'm left with my x over what I was dividing by. So my 2x, or sorry, my x squared plus 2. So I have just changed this problem from the integral of what we started with to the integral of when we divide them. So the integral of x squared minus 2 plus x over x squared plus 2. And this might look more complicated, but it really is better because I'm allowed to break it up into two different integrals. So I can integrate this easy peasy, and then for this part I do want to use substitution here, just like I did in the one at the top. So for this part of it, I'm going to go ahead and take the integral and say I'm going to have x to the third. Remember, you're raising it a power and then dividing by that, and then a negative 2x. And then we're still trying to find the integral of the second part. So now substitution wise is going to be really similar to that first one. I want to choose my denominator to be the u. So that would make my du 2x dx. So that means that my problem is missing a 2 for my du. So I'm multiplying it by 2 over 2. So about 1/2 on the outside. So I've got my x to the third over 3 minus 2x. I'm still integrating with this, but I want to go ahead and do my u substitution. I'm going to have that 1 over u du. And now I can go ahead and integrate. I get that natural log of u, but I'm going to go ahead and replace it because I'm running out of room here. So my natural log of the absolute value of x squared plus 2. And then always, always plus a very tiny c. Ran out of room there.